Thanks, Hugo. So my talk will be about my latest work, density estimation using real NVP. And so first of all, this is a work that has been done in collaboration and thanks to discussion with other people. So here are their pictures. My work is on generative model using deep neural network, and it's a work that is in a context, right? And so in this context, there are already several generative models using deep neural networks, autoregressive models, variational autoencoder, and GANs, and each of them have their advantage and inconvenience. And so basically, my work will have a different set of advantage and inconvenience, and they will try to strike a trade-off between all those methods in some sense. So the setup is very similar to setup that you've seen in variational autoencoder and GANs, in that you're going to have a Gaussian distribution that's going to be mapped to the data space, and conversely, when you're going to look in variational autoencoder, you have also a mapping from data space to the Gaussian latent feature space. And so, more concretely, in 2D that would look like this. You have an original data and it's going to be transformed like this. And so basically this way, from here, from data space to latent space, it's going to be something that is very reminiscent to Gaussianization and ICA, whereas from latent space to input space is going to be very reminiscent to variational autoencoder and GANs, and my work will be very similar to these models in that respect. So how are we going to learn these kinds of models? It's going to be learned using maximum likelihood, and we're going to have constraints on the function that we're going to define. So I'm going to define a function f that goes from input space to latent space, and this function f will be constrained to be invertible. And so once I'm going to constrain this function to be invertible, we're going to be able to use the change of variable formula to compute the log likelihood, the likelihood. So if we call z the image of x using f, then we're going to have this formula. So that gives us the likelihood of x. And so we see that it's divided in two parts. One part is the likelihood in the latent space, and the other part is the Jacobian determinant of the function f. And so I just color-coded because this part will be very easy, and that is because we're going to define it ourselves. And in our case, it's going to be something as simple as a Gaussian. For f, the function f will be neural network because that's what our labs do. And the problem with deep neural network is that defining a Jacobian for a neural network can be very difficult to compute, very expensive to compute. And computing the determinant of a very large matrix is also very non-trivial. And so basically, we're going to have to impose some constraint on f to be able to do this learning tractably. And that's what I will be talking about. So a simple case of a tractable f will be, for example, a linear model with diagonal matrix. And computing the determinant of such mapping is very simple because it's basically the product of the diagonal, right? And so the architecture that I'm going to define is called coupling layer, and it will be basically a conditional linear mapping with diagonal weights. So for that, we're just going to define a partition of the input space, as in we're going to define a set of dimension, well, two subsets non-intersecting of the input space. And then we're going to define the coupling layer with the following equations. So one side will remain unchanged, and the other side will be a linear transformation of x2. And the parameter of this linear transformation will be a function of the part that wasn't changed.
Sorry, so x is the latent space and y is the observation space?
It's well, we'll see that it's going to be both. But
is x the thing with the Gaussian distribution on it?
Sorry?
Is x the thing with the Gaussian distribution on it?
No, it will be the input space. X will be the input space, and y will be an intermediary space. So for now, I'm just defining here a function.
And what's s? And t?
So this is like y2 is a function of x2, and it's like a linear function, and basically s is just any function. S is basically any function of x1, and t is also any function of x1.
So a basis.
Sorry?
A basis. Like a basis, like regression basis.
This
is going to be a neural net.
Yeah,
TNS is going to be.
That's what I was asking. What S and T are.
Oh, okay. It's a deep neural network, for instance, but it can be any function. You just need to have the right interface in order to have the same dimensionality of x2 as for the output.
Okay.
So the output is the same size as x2.
Yeah.
The output space or the image of function t and s is the dimensionality of x2.
Exactly.
And this is going to be a useful setup for doing something with it.
Exactly. So yeah. So
we
this,
assume that it's differentiable, or
yeah, we're gonna assume that S and T will be differentiable, and that's all we're gonna need.
Bijective, probably also.
No, it's T and S don't need to be bijective. It's the whole thing is gonna be bijective, as I'm gonna show you, regardless of T and S. So yeah, and this will be our building block for the function f that I've told you about before. Okay, so this can also be defined through binary mask. Like a partition can be, like a partition of two subsets can be defined with binary mask. But yeah, okay, the most interesting part with this coupling layer is its property. And so there are the two interesting things is that the tractable Jacobian determinant of a coupling layer is tractable. So here is the reminder of the equation. And so the Jacobian has this form. And so it's basically the identity matrix here. And this will be a diagonal matrix with diagonal coefficient exponential of s of x1. And this can be anything, and it won't matter because this matrix is triangular. And so because of that, the determinant of such matrix is tractable.
But if S isn't bijective, this has a determinant 0, right? Because
no.
that lower bottom, that lower right corner, right, is a square matrix that needs to be...
This?
Yeah.
Oh, it's a diagonal matrix, and the coefficient of this diagonal matrix is exponential of s of x1.
Yeah, but if S is not bijective, right, then that will not be, that will be a singular...
As long as the entries are positive,
yeah, so
this
like
matrix has a determinant, right? Which is what we want here because that's what we'll need.
Oh, I see. Yeah, okay, that's fair. That's right.
Okay. So yeah, and so like the determinant of this matrix will be the product of basically exponential of s of x1, and the other cool property of this coupling layer will be that computing the inverse will be very conceptually easy, and it will be pretty much a coupling layer itself.
Sorry, why isn't there a multiplication by, why isn't the chain rule
Sorry?
in when you're saying the derivative of y in terms of x?
Yep.
And in that bottom right corner, I mean, it's probably just me being dumb, but like, why isn't there multiplied by the derivative of s? Why isn't the chain rule appearing here? Because is that, or is that what, or I guess that's the bottom left corner, right?
Yeah.
Okay.
Okay. So, okay. And so given this equation, we can rederive from y1 and y2, we can rederive x1 and x2, and in a pretty simple way. And so the tractable Jacobian determinant will be very useful for tractable inference and computing tractably the log likelihood of a point using our model. And having an easy inverse will be very useful as to sample from our model. And so this is, the inverse transform sampling part
So,
of the
so
model.
the tractable Jacobian, so here you've defined a function that goes from input to the latent space.
Yes.
Or like one of the components of that.
Mhm.
The tractable Jacobian means that we'll be able to compute P of x because it
Yeah.
involves the Jacobian.
Mhm.
And easy inverse, the fact we can invert it means that we will be able to sample because we can generate from the latent space and then go through the inverse of that function to the visible space.
Exactly.
Correct?
Yes, that's correct.
So what's the complexity of, what's the computational complexity of this determinant then?
Of this determinant, it's going to be linear with dimension. Or well, there's like the complexity of computing S, and then it's going to be a linear complexity with dimension, with the dimension of y2 basically, because it's just
But
a product.
dy2 dx2, is that?
It doesn't count in the computation of a
Right.
determinant of a
Yeah.
triangular matrix.
Yeah, cool. Yeah, of course. Yeah.
Okay, so a coupling layer has all these nice properties, but unfortunately there's a problem in that a coupling layer leave one half unchanged. But there's an easy way to get around this, and it will be to basically compose those coupling layer. And so here, for example, you have one coupling layer, and then you're gonna put another coupling layer on top of it, which will change the part that was left unchanged before. And you're gonna keep going on like that,
So
basically.
the new y1 becomes the x2, is that right?
Exactly.
Like the next layer, and then so you switch. Okay, yeah.
Exactly. And so by composing those coupling layers, you still gonna conserve those desirable properties that coupling layer have, because we have this property for Jacobian and determinant, and which is basically that the Jacobian of a composition is the product of the Jacobian, and the determinant of a product of matrix is the product of determinant. And the other thing is that for inversion and sampling, basically going from Z to X, we have that the inverse of a composition is equal to the composition of the inverse in reverse order. And so, okay, so basically we're gonna have, we have like first results. We initially have first result with fully connected models with S equals 0.
Can you first say something about the capacity of this relative to like fully connected layers?
Oh, you mean like of coupling layers?
Yeah, so that is like what's the like for example the set of functions captured by a multi-layer perceptron, right, is like extremely well characterized. But what's the set of functions captured by this family?
Unfortunately, I wasn't able to derive a characterization.
Or just tell us about like how many, like, I mean, does it contain like even intuitively, like how many layers of this do you need before you get something that has the same capacity as a multilayer perceptron? I mean, just intuitively.
You will. My take on this is that basically you will never be able to have the same capacity as a multilayer perceptron, and the reason for that is that you're going to be constrained to bijective functions, right? Whereas multilayer perceptron can approximate non-bijective functions.
Okay, so here's a simpler question: if you just said you're going to have a fully connected square weight matrix and some nonlinearity that's like, you know, whatever your favorite sort of bijective nonlinearity is, and you just had that, then how many of these would you have to have? N of these, basically same dimensionality. Is it basically equivalent to like applying one linear transformation per stage, or like what's the? Does that make sense? Like if you have, imagine we had a single layer neural network that's square, right? So so it has one big square matrix inside. Let's assume that that square matrix is invertible, and it's and then like, you know, tangents or something on the end. The question is like, how many layers of this would you need to be able to have the same set of functions as that class of bijective things?
Okay, so we attempted to do so. Well, we attempted to analyze this using block LU decomposition type of analysis. The problem with that is that we only ended up analyzing the Jacobian, and then like transferring the analysis of the Jacobian to the function itself becomes tricky, right? So intuitively, so it's good for intuition, and it has been used like to design our model, this use of block LU decomposition, and how we can like do some like algebra and matrix manipulation in order like to obtain something, to obtain any matrix. But once again, like the problem is that these analyses are done on matrices, on like the derivatives, and doing the transfer to the function space is, well, it's not easy.
So, well, if you just count parameters,
yeah.
How many? I mean, is it basically? So, how many parameters are in one of your layers?
In one of the coupling layers,
yeah,
well, it can be as big or as little as you want, right? Because S and T are arbitrary functions, right? So,
well, let's not call them arbitrary functions. Let's make them like linear plus nonlinearity, which is right, because that's what
it's going to be like a.
I see. So
it can
be a deep neural network.
So you can. So if you make that really complex, then like, what's the? Yeah, I guess that's kind of my question. Is like, what's the? So
you can definitely match the number of parameters.
Yeah. So I guess here's the conjecture, which is that you need like a linear node. You need as many layers as you have dimensions in order to recover that functionality, right? I mean, the functionality of a single fully connected thing, right? So because it's basically quite. I mean, so then what you would be doing is essentially saying that you can sort of dial back the amount of complexity you actually need in order to make that determinant easier to compute. I mean, this seems like the core question, right? Like, how much are you giving away by, like, you're saying I can now compute this thing easier.
Yeah.
Like, so what's the trade-off?
Okay.
I guess is maybe a more direct way to ask the question.
I see. Yeah. And unfortunately, I can't. Okay, so like I would say the trade-off with respect to autoregressive models, for example, like there's the pixel RNN and pixel CNN models, right? And the trade-off with respect to these kind of models will be that that for inference you're gonna have with pixel CNN and pixel RNN you're gonna have a higher ratio of computation to memory, whereas like for my model we're gonna have like it's gonna use more memory for less computation, and that's basically one of the trade-off we're striking right now.
I guess I mean between the architectures. Like you're proposing an architecture to replace the really obvious bijective thing with the statement that it's not cubic.
Mm-hmm.
And so now it's not cubic, it's faster.
Yeah.
That makes a lot of sense. But the model must, so I'm kind of asking, is that model smaller? Like, you know, I mean, it kind of must be smaller. So I guess, so in what way is it smaller?
and it's okay. So it's gonna be smaller. Well, it's smaller in the way that it's like it's kind of a factorization. So you're kind of learning a factorization, right? In that like you're well. Like, and once again, I'm gonna go back to the analysis that like the block LU decomposition that I've talked about is that you can have like you can decompose any matrix in like in a recursive block LU decomposition basically, but it's gonna be yeah, I'm trying to find like the right word for it. So you're gonna factor the matrix in a block LU decomposition, and it's you're basically gonna have like I think that you're gonna have like, well, first of all, you're gonna have more depth for like the same capacity, and which can incur some problem with like backpropagation, right? It's easier to train like a shallower model than like a deep model.
I just mean the functions it can represent. I mean, ignoring just the training, like it can represent a set of functions, right?
Mm-hmm.
And it must be a smaller set of functions.
Okay, yeah. And for that, it's not known yet. I've tried some analysis, and there's like this intuition of block LU decomposition, but once again, it remains to be done.
Is it universal, like in the same way that like an MLP is universal?
Well, once again, it can't approximate like non-bijective functions.
Yeah, but if you have like within the set of bijective functions.
Okay. And for that, I don't know. I don't know how to make an analysis like to approximate any bijective function, because it's not like an analysis for any function using any non-bijective function using an MLP, because like the analysis is basically doing like just doing local approximation, right, with a super wide shallow neural network. Yeah. And the fact is that since you have this extra bijective constraint, the analysis is less, it's gonna be more tricky.
What's your guess? Do you think it is?
My guess as for like how much you can approximate, I think that it might require like a logarithmic depth, like a logarithmic number with respect to the dimension, but it's like pure hypothesis, right? Like without a proof, I could make any claim.
I'm just curious.
Okay.
I mean, basically, I'm just curious, like how big these.
Oh, okay.
Well, do you think you'd get a sense if we saw the examples and then what that would look like with,
yeah. So yeah, like so empirically it can approximate like a lot of distributions, well, a lot of image distribution at least, and as like for any distribution, that remains to be seen. Okay, so so like there's this first result with like fully connected layers and with this S equals 0, and so we get something pretty reasonable, both in terms of samples, but also in terms of how it learns like a continuous latent space.
Was that just interpolating in the?
So it's basically I'm taking a sphere in the latent space, and then I project it into the input space using the function g.
So, there's been a lot of density models proposed for it in this, like over the years. So how does it compare in actual log prop?
So there's been several. Yeah, so there's been several density model. Well, no, probability model for discrete MNIST, and so my model, the model that I'm presenting right now, has this constraint that it can only be used with continuous space. Right, and so basically it makes like the log likelihood not comparable, right?
But I feel like at least Ian Murray found that like a mixture factor analyzers, for example, was very hard to beat. back when like people were using RVMs for density estimation.
Okay, so yeah, okay.
That's mixture. It
I
would
know.
be a
The
discrete,
There's like the deep.
but then you can compare it with an RBM.
So for
So I mean a Gaussian one.
Yes, yeah.
So-
I don't know how.
I compare it for TFD with the deep mixture factor analyzer, and the fact, but unfortunately, we noticed that a deep mixture factor analyzer can be beaten by a Gaussian.
I don't mean a deep.
Oh, okay.
Factor analyzers.
But yeah,
I just
okay.
mean a mixture factor analyzers. Like,
And so, okay.
it's just a Gaussian mixture model, basically, with a particular sort of reduced rank parameterization for the.
Okay, so it's okay. So like,
I mean, do you have a table with like log prefs, I guess, for against other models?
Well, unfortunately not here. But in the paper, in my paper, NICE nonlinear independent component analysis, there's, as you mentioned, there's like there's a table of log density that compares some models. Okay. So we also do some in-painting experiments, and basically we're gonna have an observed part of the input and a hidden part, and we're just gonna do stochastic gradient descent. And so it's basically we're gonna have this input and we're gonna hide part of it, and then we're gonna do like gradient descent on the log density in order to obtain like this kind of reconstruction, which seems reasonable.
Can you repeat it?
Okay, good.
This is fully connected.
This is fully connected. Yes. Okay.
So do you evaluate in painting on like RMSE or
Uh,
log? Do you assign conditional log prob on the?
So for no, the reason is that like so this is just like to obtain an in painting, but there's like you can obtain, so the model is tractable like to evaluate log likelihood on a full vector, but it can tractably evaluate log likelihood, like it can
Conditional.
do, yeah, conditional on
So, sorry,
So-
I
of
think you're just asking, have you taken the slice that you deleted
Yep.
and looked at RMSE from some
well,
target?
I mean, RMSE doesn't take advantage
or
of
whatever.
yeah.
RMSE doesn't take advantage of it being a density model. So
Yeah.
but like conditional, so you can't compute a conditional distribution.
No, we can't. Yeah. So this is just like to show that like you can have something reasonable with that.
Can you
But-
do
but-
marginals? Like if I give you, can you train on the whole thing and then ask questions about the marginal density of like a subset of the pixels?
No, neither. Okay. Okay, so like basically this, yeah, so this is Diana Walsh, but basically this kind of like this model exploits like patterns of tractable models that have been observed before actually. So for
Sorry, go ahead.
Okay, so for example, if we look at autoregressive models, we notice that so the directed graph associated to such model is actually also triangular, and it's more obvious with in papers like MADE or PixelRNN and PixelCNN. The other thing that you can also observe this pattern in variational autoencoder actually, because you see that the architecture of a variational autoencoder ends up under a certain lens, very similar to a coupling layer architecture, because if you basically in short, variational autoencoder does maximum likelihood on X joint with epsilon, which is like the auxiliary random variable that they're using for the reparameterization trick. And so yeah, like you see that there's this pattern of
When you say it's doing maximum likelihood, jointly, you mean at inference time, or
at training time? Yeah, it's doing. So basically,
like
if
maximizing the marginal likelihood of just the data?
it's doing it's doing maximum likelihood of x and epsilon, and so more in detail. Like basically, if you look at how the variational autoencoder from epsilon and x obtains z, the original paper, it's basically a coupling layer, and hence the mug picture. And so then when you go from z to like the residual of x, like if you infer the condition, the mean of x given z, for example, then it's also a coupling layer architecture. And if you have z given x being a Gaussian distribution, then you basically end up having like a Gaussian distribution in the end. And so it ends up being like a 2 coupling layer architecture for maximizing, for learning the distribution, the joint distribution of x and epsilon, if that makes sense.
So wait, so which one is like learning a joint on x and epsilon?
The variational autoencoder.
But well, I mean,
So
plus the KL, hence it's actually
it's actually learning a lower bound. But also this equation also explain how it relates in that it's so if you take the joint log likelihood of x epsilon and then you subtract the entropy, then you obtain the said lower bound on the log likelihood of x.
Right.
So yeah, so this is the point is that the point is that like it's also this model also exploit like this triangular pattern, but in a different fashion. Okay. So yeah. So like the samples I shown before, like the CFAR10 sample weren't that great, and so I basically tried like to scale up this model to like a larger data set of images, more challenging data sets, and so like I was trying several techniques to learn like long-range dependencies and image structure, and so a first simple change was to use as S and T a deep residual convolutional network, but there's also like other techniques that I've used. So it's basically like some reshaping that is present in like other models, and so it's basically transforming space into channels. And this is related in some sense to striated convolution, for example, and dilated convolution. And basically, like it's more the greedy detail of the architecture that I'm describing here, right? And so, so basically, I'm using like a coupling layer with this checkerboard pattern, and so like as described before initially on the coupling layer, we can define a coupling layer not just using partition but also binary masks. And so here I'm using a binary mask that is a checkerboard that follows a checkerboard pattern.
That's defining x1 and x2, right?
Exactly. Yes. And then I'm doing this reshaping operation, and I'm using a different partition, and I'm gonna keep doing like like using coupling layers operation using that new mask, like this new partition, and then I'm gonna keep doing this again and again. The problem with carrying all the dimension from one layer to another is that it ends up very expensive. in terms of parameter and memory and computation. The other problem is that since you're moving everything to the Gaussian latent space through a very deep, what ends up being a very deep neural network, it makes also the model more difficult to learn because you only have like a very deep neural network. And so to alleviate that kind of problem, I'm using something that I call factoring out variables. And so basically what I'm doing is that I'm gonna first go through a first sequence of transformation, and then I'm gonna exclude a part of the dimension which will be directly used that will be directly considered as Gaussian, and the other part will go through another cycle of transformation. And so the advantage of such factoring of dimensions will be that it's gonna ease the learning, and that's because it's very similar to deep supervision in ImageNet models, for example, that you have, for example, in Inception. And it's gonna use like less parameters and less memory and less computation because I'm not gonna carry the variables like all the way through, right? So yeah, and conversely, when you're gonna sample and invert the model, you're gonna first generate from a Gaussian, and then you're gonna go through this reverse cycle of transformation, and then with this transform variables will be concatenated with Gaussian variables, and this concatenation will go through another cycle of reverse transformation. Okay. So to facilitate the learning of the model using gradient descent, we're going to use additional techniques. And so there's the usual techniques like residual network, batch normalization, and weight normalization that were used. But I also used an extra approximation, which is basically using batch normalization for the random variables. And so if we estimate the variance sigma square and mu, and the mean mu, then the batch normalization transformation is basically this, and we will make the approximation that this transformation has a Jacobian determinant of equal to the inverse of the denominator. And this also helps in great length the learning of the model.
So the equation x from x normalized, that's a regular batch norm?
That's basically, yeah, that's
regular batch norm, but then you're saying essentially that the gradient you instead approximated using that. Is that what's going on here? I will basically take batch normalization as a component of f. And so for that, you're also gonna need like not only the forward prob, but also the Jacobian determinant. And this is basically the approximation that I'm doing, in that I'm considering the Jacobian determinant to be this. Okay, and how does that impact your estimate of the real density?
So for training, it's going to be inexact.
Okay, but once and for all, you estimate the moments and then
exactly
do the exact thing.
As regular batch norm, you accumulated some moments, and then you use these final moments to evaluate log likelihood. And this is basically just a linear transformation with diagonal matrix, right?
Gotcha. Okay.
Okay. So this is like the qualitative result, and so we can see that it's pretty competitive with other methods, although it's not beating like strong models like PixelRNN, for example, and PixelCNN. It remains relatively on par.
How do you deal with, remind me how you deal with the pixels being discrete here? Gaussian noise? Is that what you do?
Yeah, okay, yes. So we're using like, it's basically
Not
using
Gaussian, but
RNA.
uniform noise?
It's uniform noise, yeah. I'm using uniform noise, and I'm basically following the guideline that is also described in a note in evaluating generative models.
Okay, cool.
So, sorry, how are you, so these are accuracies or error?
Oh, sorry, these are bits per dimension,
Okay.
yes. So so this is like a log likelihood numbers, and this is the unit is bits by dimension. Okay, and so this is like the more qualitative results, and so you can see that that the samples are relatively sharp, and the reason for that is that as opposed to other models like that relies on reconstruction error, well, this model doesn't rely on reconstruction error. It's on a fixed reconstruction cost, and that basically help the model, well, allows the model to learn something that is maybe more perceptual in some sense.
Sorry, so these are all, you said these are all samples from the model?
Yeah.
So I've always been curious, I mean, when you see images like this, I mean, have you done a search in the training set to see how similar these images are to a particular training example?
What would you use to do that?
Yeah.
You could either embed them in the latent space or then look for them in the latent space, so that then you like see if they're the same, you know, I mean, you could do it in pixels, but also, because, you know, I mean, it always surprises me how sharp some of these kinds of things are.
Yeah.
And so I feel like a kind of a due diligence on any model like this is to ask the question, how close is this to the closest training example?
Okay.
But here he has log probes though. So unlike things like GANs, where you can't get any good estimate really of log probes, at least he knows he's not like overfitting in an insane way.
Sorry, how does he know that?
Because the test set log probes are not like really, really bad. Well, relative to other things.
They would just be big. I mean, the test sets, yeah, so in the test set,
If it was only generating training examples, the test set log probes would be really bad because he has the real log probes for his model, right? Unlike GANs, which can't really give you a good estimate.
yeah, no, that's fair. I guess, but you could imagine that it's just basically putting like little, it's like smoothing the test data, right?
Yeah.
So this is doing. Do you have number? Are there numbers
I'm not
for
saying
single
this is a problem,
Gaussian?
but I'm saying these look so much like training data that it seems like a due diligence would be to just feel comfortable that, like if you put every one of those images, if you looked at the latent representation that you sampled from, and you looked at the training data and embedded the training data and then looked to see who was the closest, whether or not you would basically get the exact same image.
So you're doing well enough to like spark skepticism.
Yeah.
So what I would do.
So that may be amazing, right? That's the answer.
The visualization I think would be great. So if you got rid of 2 panels in type 1, you made it double wide and then had these pairs of images, which is your generated image, then the nearest neighbor in your latent space. And then a cool like video you could overlay on that is I would love to see. I've never seen this before.
I have perturbation.
Exactly, yeah. So like have an orbit around your sample point, and then see how their sample image changes. Because
okay.
If you can smoothly interpolate between stuff, or like.
So this is what I'm gonna show later. So this is like yeah. So this is okay. These are just the samples. But also like for image they're good. They're sharp and they're coherent. But there are other models that, like sample-wise, are debatably better. Like for example, GANs.
But I don't believe that. I don't believe those results either. I guess.
Yeah. Okay. And so,
just to be clear, I've never seen anybody do this when they show like very nice pictures of generated faces.
And there's also like okay. So I'll take this opportunity to also point out that there's. Also, another possible family mode with generative models is to only model a subset of it, which like is very convenient. Like when you have limited capacity, if you want to generate very nice looking samples, But the fact is, because these models are trained with log likelihood, and you can actually measure, like, log likelihood penalize very strongly when you miss something, right?
Yeah, I mean, the problem is fundamentally ill-posed, right?
Yeah.
I mean, just to be clear, density estimation is an ill-posed problem.
Yeah.
Right? I mean, it just is, because the actual maximum likelihood estimate is the empirical distribution of your training data.
Yeah.
Right. And so everything you're doing is regularizing away from that in order to make the problem not ill-posed. Like bandwidth and Parson windows or whatever it is, like there's some knob you have to choose always in density estimation that reflects essentially your smoothness assumption about the density. In the absence of that, the maximum likelihood estimate is just like a bunch of delta functions on your training data.
True. Well, although like your point also hold for like classification, like the solution is nearest neighbor, right?
Well, it's not necessarily. I mean, yeah. So I guess density estimation is kind of like worse, right?
Yeah.
In a sense, right? Because essentially you know exactly what the maximum likelihood estimate is always a priori.
Yeah.
So just out of curiosity, if I told you that, I actually don't have this result, but if I told you that a single Gaussian had worse log probs than this model, does that answer the question that maybe it's just overfitting on the training set or not?
I don't know. I'll have to think about it.
But I'm wondering about that. Because I'm pretty sure that numbers for a single Gaussian are really bad, and you don't expect it to generate anything close to that, right?
Yeah.
But you almost actually want to place your model on the spectrum of like K, for like how many components do you have in your GMM to model this space, and like where does your model fit, right? Because you can do arbitrarily well once you have like K is equal to the number of data points.
The training set, but not on the test set. You can do horribly on the test set. Yeah. Like to me, that's the biggest sanity check of a method like this on like GANs. At least it doesn't tell you, oh, but all the test set has 0 probability. Yeah. So then you're like, well, of course you're memorizing the training set.
I mean, that seems.
Okay, so also I told you that I'm gonna show you interpolation, and I'm delivering. So this is like this whole. There's a lot of thing going on. So this is like you will be able like to check this out later on, but this is basically examples, samples, and then because the model is convolutional, you can basically try to generate bigger images and actually see how the model fails.
So you're going to show us a path between two tests.
So yeah, and so this is actually path with several test examples, right?
Can we see it?
Sorry?
Can you make it bigger, please?
Sure.
On the size that it was trained on?
Yeah.
So what is happening?
Yeah.
So okay, maybe wait. I'm just trying to see.
There's an insect on the bottom.
Oh yeah. So like there's basically like there's basically a bird on a hand, and there's basically a music instrument. This is like a fridge with several bottles.
Oh, that's actually an image from it.
Yeah.
Sorry, we're going top to bottom?
Oh no, it's interpolating with several images.
Oh.
So there's several images with which you interpolate, and so like you see that it like. I mean, as like for ImageNet.
So which ones are the ground truth?
Yeah. Which one are real images?
So these,
Oh,
and these.
Okay.
And
anything
so,
in between is interpolation.
Yeah, and so well, you can see that like several of these images like, and so I basically so I basically take 4 points and I do like a interpolation between them. And this part is extrapolation in some sense. Sorry?
Real images.
Oh, so these corners are basically ground truth,
right.
and then it's basically it's like an extrapolation, like a circle extrapolation. Like basically, like this is very similar to this, and the reason is that it's basically stitched together.
Oh, that's
Like
a sphere.
I'm basically sort of taking a sphere, taking those points, and I just map back this sphere in the latent space back to the.
But so
Sorry,
interpolating then is not a smooth path.
You mean
a linear path in your latent space?
Sorry?
Right, so can you point at there are 4 real images here, right?
Yeah, here,
One.
here, and here.
Okay.
So you have 4 points, and then a sphere is sitting on top of those points. So then going from one to the other on the top line is not a linear path.
Yeah, that's
Your
not a
latent
linear
space?
path. Yeah.
Oh yeah. What
It's
would be
like
really
your-
cool to see is to take 2 training points
Okay.
and then just go right between them.
Oh, okay. I see.
Yeah. Something like that.
Is it a blend with like the cosine or something? Or the sine
Yeah.
or something?
It's basically a cosine interpolation. Yeah, and you can. So, I mean, between like these looks like images for ImageNet, but it's obviously like not something real. But like for ImageNet, you see that it capture like the statistics of ImageNet, but these are not fooling anyone, I would say. At least from closer distance.
So if you draw samples, this means if you draw samples from this thing, you'll always wind up with garbage? Stuff that looks like the interpolated examples?
Sorry? Oh, I mean this. Yeah, I mean you sample something and it's basically not gonna be. It's not. It's very likely that it's not gonna land on a point,
Yeah,
right?
so why do the faces, is just the faces or a much smaller space? Is that the...
Sorry. Oh.
Yeah, what was
Oh,
so good at faces? I think
Oh.
this is the question.
I mean because like.
Less variation?
Hmm?
Less variations between
Yeah,
faces?
there's less variation between
What's
faces,
the
and
size
it's like
of
very.
celebrity?
So it's 64 by 64.
And the number of data points in the training set? Remember?
That I don't remember. I don't have it in mind. Is the Celeb A dataset? I could look it up right now.
It's okay.
But okay.
That's good.
But yeah, it's the fact is that like Celeb A has less variation, has a lot less variation than ImageNet, right? Because these are all centered faces, as you can see here, actually.
Can we see the bedrooms?
Sure.
That's right. Hello.
So yeah, and like bedrooms in the same fashion, like doesn't have the same amount of variation as ImageNet.
But it's still more than faces.
Sorry?
Maybe it's still more than faces.
Yeah, yeah.
Oh, the bedrooms are freaking impressive. Well, when you zoom in, they're not, but
Yeah.
I'm.
From distance, yeah.
Yeah, and so like I mean, it's the same goes for like the tower category and the church category, in that it's very it's the distribution is less diverse than ImageNet, and so you're gonna have it's gonna be easier to model, and that's why it's better for demonstration.
Did all
but-
of these have the same capacity model?
Yes. Well, for this, for all 64 by 64, so from here you just have 64 by 64 images, and these have the same capacity. The capacity is basically limited by memory on a K80 GPU, with not that well optimized code, and like the 32 by 32 ImageNet has smaller capacity. Yeah. So yeah, okay, back to this. Okay. So yeah, you can see that the model have like capture sharpness and a degree of global coherence. It also capture like some notion of background, foreground, luminosity, and shadows. And yeah, it also it's basically obtained tractable, like a competitive likelihood result. And the fact is that this model is pretty fast, both for inference and also sampling, which would be useful if your end goal is to sample fast. And so yeah, there's possible future works that I'm gonna lead shortly to. So basically, this what I've presented is like this set of invertible functions that are very compatible with probabilistic settings, right? So it can be combined with like other probabilistic model, continuous probabilistic model, pretty smoothly. And the other thing is that these invertible neural network structure can also be used for other applications than probabilistic models. Like you can basically learn a feature space that follows, different properties than just probabilistic properties. So yeah, that was my talk. Thank you for your attention.
Thanks.
Yeah.
What's the thing about function? I see the last point. Functions with tractable arguments. What do you mean by that?
So basically, there's like some there are like some function, like there's for some application like Q learning, you want to have a Q function, continuous Q learning. You're gonna have a function that is tractably.
So the best action.
Yeah, exactly. And so, like right now, what people have been using was quadratic function, but with this kind of setup, you can extend it to something less linear.
But why is the argmax tractable?
Oh, the argmax is tractable. Oh, okay. So basically, if you like, if you map something to quadratic, then you just maximize in the quadratic space, and then you just map back. It's.
Oh, well, because it's invertible, and then okay.
Yeah.
Okay, that's interesting. Have you looked at semi-supervised learning or like? See whether, because some of the examples are pretty good, and there's a latent space, so that suggests actually using the forward pass as a future representation of sorts.
So we're looking at it right now.
Okay.
We're doing this with Jasha. So
because a lot of this work on generative models is partly motivated by, well, if you have a good generative model, then perhaps that can help exploiting unlabeled data for some other tasks.
I see.
But I think that is potentially an application of.
Okay.
And so I was wondering whether
that's
doing
true.
Something like that.
On the other hand, like application like WaveNet, mine, like it's kind of also justifying by itself to a large extent, like.
I think it's more obvious that we want to. It's more obvious to me that we want to synthesize sounds than we want to synthesize images. At least functionally, like it's kind of funny to see these images. But,
definitely.
But I guess there's nothing. I guess I don't see it here. But you could potentially apply it to sound waves as well, right?
Yes. Yeah.
Okay.
And how hard, like, compared to GANs, is this thing?
The training of this model. I basically use the default hyperparameter of Adam, and I mean there's there's like some there's like this extra technique, like for example the batch normalization was very crucial, like to train very deep models, and this is basically the difficulty that you're gonna have when you learn like a probabilistic model with a scale parameter. You have like this multiplicative interaction that can cause problem for your backpropagation and some instabilities. But apart from that, I didn't encounter like strong difficulties in training.
But you still had to like play around with the parameters and all, right?
Sorry?
Like you still had to play around with the parameters, like hyperparameters and all.
I mean they all converged.
Oh. Okay.
If that's a question, and also
for GAN, sometimes it doesn't really convert. You're just getting rubbish.
That is what I heard also. It's a fine art, but for I played with the hyperparameter, and it's also motivated with like I have a limited budget in terms of memory and how to obtain best results.
So it's still memory hungry, like even on GPU, right? That's why you use K80s, right?
Yeah, I mean, these are, yeah, it's a very deep model, yeah.
And where do they use the residual blocks? For which part of the network do they use?
For which part I'm using residual networks? I'm using residual network so basically the S and T functions are deep residual network, convolutional.
So here, the number of parameters is probably not. It's mostly the feature maps that's just taking a lot of memory. It's not because your model, in terms of parameters, is
feature maps and intermediary computation. Yes, they do take a lot of memory. Plus, I use it's kind of my fault. I use also a non-optimized version of batch normalization, right? So if you're not careful, it's just gonna just use twice as much memory as it should.
Okay. And how
There's have you is this implemented in Theano or TensorFlow?
It's implemented in TensorFlow for now.
TensorFlow. There's a feature of MXNet which might actually be, it's not always appropriate for stuff, but I think it might be appropriate for this, which is called checkpointing. So not per epoch checkpointing, but the idea of dropping intermediate computation, the storage of intermediate computation, in lieu of recomputing it when you're in the backwards pass. So basically dropping like either the activations or whatever, and that can take the memory budget down by like 80%. Depends on how aggressive you are, and it's obviously a trade-off with compute, but it can be generally quite a good idea if you have like memory-heavy models.
Okay.
So I think it's out of the box in MXNet, but you should check it out if that's interesting to you.
Okay.
And how long does it take to train, the whatever capacity you converged on some of these data sets?
So
and you don't do distributed thing, right?
Sorry?
You don't
Single
do
distributed.
I do distributed thing, and it takes like a few days to get something. Well, like it takes a day to have something that is like starting to look like the data set, and like 24 hours, and then like after a few days, it's still training, but I didn't have the patience.
Interesting. And is there, I guess you mentioned that doing this sort of factoring is kind of like, indirect, or what do you call it? Not indirect supervision, but or direct
supervision.
Yeah.
Yeah.
Would pre-training make any sense here? Just starting with fewer layers and then adding on top of the F functions more and more. You could imagine just training the first set of coupling layers.
Yeah, and then keep like Gaussianizing more and more.
Yeah.
In the end, like you still wanna. I suspect that you still wanna train in the end, like end to end. And the fact is that like
so not keep fixed the lower layers, but maybe just keep adding capacity essentially.
You're talking about expanding S and T within each.
Not S and T, just the number of these coupling layers, where you just so you essentially have like a few steps of the shuffling, right? So let's say you train the first part, and this is not the shuffling, the refactoring, I think we call it. So you train the first part before there's any refactoring as the complete model. That's a smaller model, so it should take less time.
Yeah.
And then say converge or something, and then you start, and then you say, okay, well, I'm going to do the refactoring, I'm going to have my next, set of coupling layers.
Yeah.
And I train jointly just this slightly increased, more capacity network where this has been initialized.
I see.
Would that make sense here, or do you suspect overfitting maybe of the earlier layers, or?
So, I don't think that there's going to be an overfitting problem, but it's just that there is a non-negligible risk of like basically destroying what either destroying what the previous pre-training did and not taking advantage at all, or like on the contrary falling into a local minimum. Like basically if you have something that is roughly Gaussianized, then you have less incentive like to keep transforming more. So I had this kind of problem but once again it was like without batch normalization, without like just deep rectified network, and not even like a S function. And I have this problem of like train like I just train one coupling layer and then I add something on top of it, and it basically hurts more than doing end-to-end directly.
Okay.
But this experiment could be remade with like these extra components.
Okay, cool. Other questions?
No.
All right. Thanks, Lava.
Thank you.
Thanks.